Now let us try to understand this basic concept with a very simple example. Trust me, I will take a very simple example for this. Uh, because with this example, I'll try to clear all the concepts, all the formulas which we require for this. So, assuming that this is the main memory, this is the main memory, or main memory is also called as the physical address space. So every time, next time I'm going to use a main memory, I'm going to say it is a physical address space. And for simplicity, I'll take a very simple example. Let us assume that the size of this main memory or the size of this physical address space is 64 words. Size is 64 words. Okay, for those who don't not understand, just assume that instead of 64 words, I'm just writing the size of the main memory 64 bytes each, right? The complete memory is 64 byte. And assuming that it is representing our process, or you can say the virtual address space. This is representing our process, or you can say the virtual address space, the virtual address space, or you can say, the logical address space. Virtual address space is also called as logical address space. Logical address space, okay, or LAS. And let us assume that the size of this logical address space or virtual address space is only of 16 words. Is only of 16 words. And this logical address space will be divided into pages, and the main memory will be divided into frames in such a way that the page size will be equal to the frame size. Page size will be equal to the frame size. Okay, now let the page size let the page size is of only of 4 words. The page size only of 4 words. That means how many pages can be present in this this virtual address space. So number of pages can be found out as virtual address space upon the page size, which is equal to 16 words divided by 4 words. So you can see it is only of 4 pages. So we are going to have 4 pages. Okay, so you can divide this entire virtual address space into 4 parts like this. These are the 4 pages. In every page, we are going to have all these words, or you can say all these bytes. Okay, assuming this is a byte number 0, byte number 1, byte number 2, byte number 3, byte number 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Okay, because we have total of 16 words. See, I'm going to interchangeably use bytes and words here, because I'm assuming that the word size is equal to byte size here. So we have total 16 words which are represented like this, right? In the same way, this main memory will be divided into frames. So the number of frames in the main memory can be found out as physical address space divided by the frame size, and the frame size is equal to the page size. So it is 64 words divided by 4 words, which is equal to a total of 16 frames. A total of 16 frames. Therefore, you can say this entire main memory will be divided into 16 frames. So assume these are the frames: 0, 1, 2, 3, 4. Oh, let me do one thing. Let me draw it in a bigger, bigger diagram of this. That will be easier to draw and understand. So this is your main memory. Okay, so it will be divided into 16 frames. So it is frame number 0, frame number 1, frame number 2, frame number 3, frame number 4, frame number 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and we require one more 15. So we are having a total of how many? 15 frames, which are the frame number 0, frame number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And here we have the pages. So we have page number 1, or you can say page number 0, page number 1, page number 2, and page number 3. So these numbers are denoting the page number. These are denoting the frame number, and here inside this, these are denoting the internal words or bytes, or you can say the byte number. So in the same way, how the virtual address space is divided into 4 pages, and size of each page is of 4 words. In the same way, the main memory is also divided into 16 frames, and size of each frame is around 16 words. Sorry, size of each frame is around 4 words. So these are the word numbers which we have. Word number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, up to so on. Here we'll be having 61, 62, 63, and 64. So it will be maybe 60, 61, 62, and we'll be having 63. So this is the word numbers, right? So what generally happens is, in case of this memory paging, we can take one page. For example, we can take this entire page, and we can place this entire page inside a frame. So you can see this entire page can be placed inside a frame like this. Okay, so assuming this page is placed into this frame, so there is a mapping between a page and a frame, and we are going to use something called as a page table, which will tell us what page is stored inside which page or which frame inside the main memory. So let me draw that. So we are going to use something called as page table. This is representing a page table, and in this page table we are going to have entries, because for every page we are going to have one entry. So this is the entry for page number 0, this is the entry for page number 1, this is the entry for page number 2, and this is the entry for page number 3. Now in this page table we are going to store the address. For example, these are the addresses of frames. So this is the frame number. We are going to store the address that this particular page is stored inside this frame. For example, just for simplicity, just assume that I'm going to place this page number 0 into frame number 4. So page number 0, if this is representing the page number, then I can say the page number 0 is placed into the frame number 4. In the same way, I can say the page number 1 is placed into frame number 6, page number 2 is placed into frame number 12. In the same way, I can assume that page number 3 is placed into frame number 15. So this page table is going to store what is the frame number where that particular page is placed. Okay, now you answer me the following questions. First of all, you know that these particular you already know what I told you. Now there's something called as virtual address, and there's something called as the physical address. Okay, before I ask you the question, let me tell you these two functionalities also, because these two functionalities are also really very important. Without that, you will not be able to answer the questions which I am going to ask. Right, so this virtual address space is representing the entire process, and this physical address space is representing the entire memory. Now there's something called as virtual address. So let me write it as virtual address or logical address and there's something called as physical address. Okay, now this virtual address is actually the address of each byte. address of a byte, or physical address is the address of a byte, or you can say address of a word. For example, if I ask you what is the address of this byte 9 into this virtual address space. Now what will be the address of this byte 9? If you count all the bytes, or you can say if you count all the words, what is the address of this word? If you count all the words, total we have 16 words. To represent these 16 words, we are going to require 4 bits. We are going to require 4 bits, right? And with the help of 4 bit, we can represent the address of every word. For example, if this is a word number 9, it can be represented by the following address, which is 1001, right? In the same way, if we have this particular word, assume this is a word number 2, it can be represented by 0010. Why I am using 4 bits to represent the address is because in total we have 16 words. If I give an address if I associate one binary combination with one word, then we are going to require at least 4 bits to represent all these 16 words, because with the help of 4 bits we can make 16 combinations. I think that is very simple and you will be able to understand this, right? So let me tell that concept again. What I'm saying is, if you have, for example, 2 bits, then you can make 4 combinations out of these 2 bits. The minimum number is 0 and the maximum number is 3. That means you are making 4 combination. If you are having 3 bits like this, now with the help of these 3 bits you can make a total of 8 combinations like this. You can make a total of 8 combinations where the minimum combination is 0 and the maximum combination is denoting 7, right? In the case, if you have 4 bits, then with the help of these 4 bits you can make a total of 16 combination where the minimum value is 0 and the maximum value is denoted is 15, right? In the same way, if you have n bits, with the help of n bits, the minimum value will be 0 and the maximum value will be 2 raised to power n minus 1, and in total you will be having 2 raised to power n combinations, right? Now in this previous example, here we are having, you can clearly see, we are having a total of 16 combinations. That means we are having a total of 16 words. For every word we are going to require 4 bit to represent the address. Now let us see this address. Let us do some doctrine on this address, because we are Indians, we try to analyze everything in a greater depth. So if we take this particular address, which is 1011, now this 1011 address can be represented like this. We have the complete address, which is 1001. Now in this complete address, you can also break this complete address in one more way, and that way is saying that this 9 was actually go to the page number 2. In the page number 2, check the second word. Second word is, for example, if the first word is represented by 0, second is represented by 1, third is represented by 2, and the fourth is represented by 3, right? So you can say just to give the address of this location which we have seen here, just to give the address of this 9, there's one more way of giving the address of this location 9 is, I can say, go to the page number 2. In the page number 2, check the second word. For example, if I say it is the first word, it is the second word, it is the third word, and it is the fourth word, right? So I can say that go to the page number 2, check the second word, or numerically you can say, if I number at 0, 1, 2, 3, so the second word will be represented by 1. So check the second word here. So for page number 2, to represent the page number 2, I can represent it like this. This is representing that we are going to the page number 2, and this is represented by 1, and it is represented like this. Okay, so it is represented like this 1. So we can break this complete virtual address into 2 parts like this. We can break this virtual address into 2 parts. The first part, this first part is denoting the page number. It is denoting the page number, and the second part is denoting the particular word number inside the page. Word number inside the page, which is also called as page offset. Which is also called as, this word number is also called as, there's one more terminology for this, that is also called as page offset. Page offset. Page offset. Okay, got it? You understand this? Okay, so in the same way, if we discuss about the main memory, Now this main memory is having a total of 16 words. It is having a total of 16 words. If I take any random word, for example, if I take this particular word, if I take this random word, if I want to give the address of this particular word, to represent the address we are going to require 6 bits. Why we are requiring 6 bits? Because we have to represent a total of 64 words. That means we need a total 64 combinations from the binary numbers so that we can represent every word uniquely, right? So to represent 64 combinations we require at least 6 bits, right? So to represent this number, which is 18, how can I actually represent this number 18 is if I write in the binary, it will be 0 1 0 0 1 0. So this number in binary is representing 18, right? For example, you can see this 1 into, this is 2 raised to power 5, sorry, this is 2 raised to power 4, this is 2 raised to power 4, this is 2 raised to power 3, this is 2 raised to power 2, this is 2 raised to power 1, and this is 2 raised to power 0. So it is 2 raised to power 4 plus 2 raised to power 1, which is 16 plus 2, which is equal to 18. So you can see this number 01001 is representing a number which is 18. So let me again do this. It is 010010. Okay, you can represent it like this. Now if I want to represent the same address, can I represent the same address of this byte in another way? Yes, I can do that. How can I do that? First of all, I have to tell what is the frame number. That means in what frame this word is present. That is, for example, here the frame number 4, and in total how many frames are there? Total we have 16 frames. You can clearly see frame number 0 to frame number 15. So in total we have 16 frames. To represent 16 frames, if I give a binary combination to each frame, I require at least 4 bits. To give 16 frames, I require at least 4 bits, right? So you can see this is a frame number 4. So I can also break this complete address into 2 parts. Number 1 is the frame number, and second one is the frame offset. Second one is the frame offset, where frame number is saying this particular word is present in which frame. For example, here you can see this frame number is representing a number which is 4. That means it is present in the frame number 4, and inside that particular frame, what is that particular combination? For example, if I represent the 16 by 0, it by 1, it by 2, and this by 3. So you can see inside the frame number 4, this is the byte number 2, right? So byte number 2 is like byte number 0, byte number 1, byte number 2. So this is a byte number 2 in the frame number 4. So you can see this number is representing the byte number 2. So you can see the entire physical address can be broken down into 2 parts. Number 1 is a frame number, and second one is a frame offset. In the same way, the entire virtual address can be broken down to 2 parts. Number 1 is a page number, and second one is a page offset. Page number and the page offset. Okay, now you can clearly see the size of page. The page size is equal to the frame size. The page size is equal to the frame size. Therefore, the number of bits in the page offset will be equal to the number of bits in the frame offset. This is very simple, because the page size is equal to frame size. If page size is of 4 bytes, then frame size will also be of 4 bytes. To represent 4 bytes require only 2 bits, right? So therefore the size number of bits required in the page offset will be equal to the number of bits required in the frame offset. Okay, now if you want to store something into this page table, now this page table will only store that the particular page is present inside which frame. For example, if I say the page number 0 is present inside the frame number 4, therefore it does not require to store the frame offset. It is only going to store the frame number. It is only going to store the frame number. For example, if I say the page number 0 is present in the frame number 4, so it is going to store 0100. If I say the page number 1 is stored in the frame number assuming 6, so it is going to store 0110. If I say the page number 2 is stored in the frame number 12, therefore it is going to store 1100. If I say the page number 3 is stored in the frame number 9, so it is going to store 0101. So this page table is only going to store the frame number. Okay, now if I ask you what is the page table size, if I ask you what is the page table size, the page table size. And page table size itself is no, it's very easy to find out, as you can clearly see. To find the page table size, you have to see what is the number of pages we have. You can say it is a number of pages, because for every page we are going to have an entry in the page table multiplied by what is the number of bits required to represent the frame number. What is the bits required to represent the frame number? You can say multiplied by bits required to represent the frame number. The bits required to represent the frame number, that is called as the page table size. That will give you the page table size. Now how this entire things will actually work, let me give you a simple example out of this. See, I know this till this point of this you are already saturated by seeing this example, but I have to go through this entire process once, then we can take more examples to solve this complete this complete problem again. Okay, so you can see we have a CPU. Now CPU generally generates a request. That for a particular process I need this byte number. It will say that for a particular process, for example I am executing this process, for this process I am required the byte number 9. So byte number 9 can be denoted like this, 001. So how will that complete will be broken as? This complete address will be broken as page offset and the page number. So the CPU will then consult, by seeing this page number, CPU will then consult the page table to know that I want to know the address of the location where the page number 2 is stored in the main memory. Please tell me the address of the location where the page number 2 is stored in the main memory. So through the page table it will get the frame number. So it will take this frame number and then it will find out that this particular page is stored in frame number 1100, and it will take this page offset like this, it will add this page offset like this, and it will say that I want to access that particular byte from this particular frame number. To tell you how I want to access this particular byte from this particular frame number. Okay, so this is the entire process which we are going to have. Again, let me tell you, CPU will generate a request that I need this particular byte for a particular process. That when I'm saying particular byte is because that every instruction will be stored inside a process, and that every instruction will be having a relative address, and that relative address will be actually the physical address. The virtual address, which is the relative address, and we are going to take that relative address that will be given as this complete address. For example, instruction I will be stored at byte location 4. So I'm going to get this address. Now from this address I'll separate the page offset and the page number. I'll check the page number. I'll take this page number to the page table. I'll verify that this particular page is stored in which particular frame. I'll add this frame number and the page offset, and then I go to that particular frame or to that particular address in the main memory to access that particular byte into the CPU. So this is the entire process which we are going to use it. Okay, and this is, I think this is quite complicated. This video is too long for you to understand. It is too long for you to focus. So let me do one thing. Let me take more examples of this, and let me give you a complete table of formulas which you can use to represent this. The better way is not to remember the formulas, because if you try to remember the formulas, it will become so much confused in the examination hall. It will create unnecessary pressure. So let me, in the next video, let me try and give you a better way to derive your own formulas, because deriving is much better than remembering. That will not create pressure on your mind, and if you can derive the formulas, you can if they twist these questions in a bit, you will be able to easily solve those questions. Okay, so let me meet you in the next video.